Hi, everyone. Nice to meet you. I'm Sarah. I've been data scientist at Data Scientist since last January 2023. And today I will be presenting a workshop on multi-threading, multiprocessing, computing power, and costs in machine learning. This actually is a very basic introduction, but this might give you some information and an overview of and a mapping as well of the different techniques that you guys can use in your data science project or in your data engineering projects. I am very glad to welcome you here on this video and at Data Scientist as well. Remember that we are a training in data science with bootcamp and continuous trainings, and we provide trainings in data science, data engineering, in machine learning engineering, in cybersecurity, and data analysis as well, and multiple other tracks. And we also have a blog and a website where you can find us and also try and see if there is any training that you would be interested in. It's datascientist.com. We also have something that is a blog, Data Scientist Studio, to see some of the projects of our learners. And we also have a set of workshops on YouTube, these data atelier workshops on several subjects that are very, very good and very acute and very detailed workshops, as well as some podcasts and a blog containing articles that are really good articles on data science technologies. So we are going to wait just a little bit for the others to come in, and then we'll start around 10:05. If you already have any question, please feel free to ask them on the chat. The chat is available for you guys to make comments and talk to each other as well. And I will be presenting this session with slides, and you will see this session available with the slides available on YouTube as well after the recording. So if you guys want to go and check as well what kind of videos we have, it is actually a large set of elements, such as time series. I have a blank here. Time series, and what else? We do have time series. We do have a PCA. We have no code, Power BI. We have also, there might be an explanation on Streamlit. There is also elements on introduction to machine learning, as well as other either DevOps or data engineering workshops. And we will start in a few minutes. So now that I can see that there are many of you that have started, amongst other some of my students, I will show you the beginning of this workshop. So today, for those who just arrived, hi, I'm Sarah. Nice to meet you. I'm data scientist, and I have been data scientist since January 2023, a data scientist. And today I will be introducing some of the notions around multi-threading, multiprocessing, and computing power, as well as costs in machine learning. This idea of creating this workshop is stemming from the fact that a lot of people in my project are asking questions about how to speed up computations, and what tools could be used on what platforms, as well as if you deployed a model, how could you speed up and reduce the costs. We will first talk about multiprocessing and multi-threading, then on GPU. We'll talk about examples on machine learning algorithms and example on deep learning methods and packages. We'll make a alias on storing a lidar model and create a script for PyTorch, PySpark, and ETL. Talk about monitoring, good practices for reducing computing costs in code, and the impact on billing and workflow on the cloud, as well as a little conclusion that will talk about all the previous elements that we have flown over. So let's start with multiprocessing and multi-threading. On this journey, we'll talk about these elements on an MLOps or MLE viewpoint. MLOps, machine learning operations, and MLE, machine learning engineering. There are going to be loads of definitions. The first one being what a core is, RAM, a CPU, GPU, SSD, and HDD, asynchronous and synchronous tasks. What is a task? What is a thread? A process, a program. What is I/O bound, disk, multi-threading, multiprocessing, cluster, nodes? What are locks and synchronizers? What is race condition? Deadlocks and semaphores, distributed architecture, CUDA, NVIDIA, TensorFlow, Keras, CUDF, and memoization. So basically, when you're hitting a machine learning problem, where can you speed up? You can speed up in loading. It appears when pre-processing the data, as well as in training the algorithm. And when you have a lot of data, you use frameworks, threading, or generators in order to load the data or load part of the data and speed up this loading and training of your algorithm. It's also in the computations. So pre-processing, as we said, in feature engineering, in data augmentation, in training, in predictions, in saving the model and results, in the metrics, and in the monitoring as well. You also have this problem on device, either if you're working on a single device or a set of clusters and machines in a distributed architecture, or if you're working on premises or on the cloud. And this is going to be taken into account in our journey. So first of all, the components. We're going to dive a little deeper into your computer. Your computer has a CPU, and CPU have cores. So a core is basically unit processing unit in a CPU, central processing unit, and it's responsible for executing instructions and performing calculations for various tasks. And these processes can be done simultaneously. It means one on each of the cores. So let's say you have a task here, and a task here, and a task here, and a task here as well. I will just make sure that you guys can see the... I'm actually not sure you guys can see the mouse on this. So I will just make a little pause. Settings, I think not. But that's all right. And we have a shared L3 cache, that is basically the cache of the CPU, and a memory controller, that is the memory of our CPU, central processing unit. CPU have dual core, for instance, or quad core, or 6-core, octa-core, multiple cores, and this is what a CPU chip looks like. We also have what RAM is, and VRAM and disk. RAM is random access memory. It's a form of electronic computer memory that can be read and changed in any order. That could be used for storing data or machine code, so storing working data. You use it in machine learning with large data sets as a high-speed storage medium and additional and intermediate storage. You have GPUs that are often that have often their dedicated memory, that is the VRAM, and they are separate from the RAM. So the GPU has its own RAM, and you have a RAM that is separate, but sometimes the GPU can use the RAM that is on the side. You have disk data access. You have storage devices such as hard disk drives, HDDs, or solid state drives, SSDs, using for storing data on a computer system. You have HDD that have a moving part that make them more fragile to shocks and is cheaper than SSDs. And that is actually an alternative to RAM. These are actually other vocabulary words, NVMe and PCIe, Peripheral Component Interconnect Express, that enable the communication between the solid state drive and the CPU. And you also have a cache in the CPU that is memory of the CPU, or at least that is a cache memory of the CPU. You have also different kinds of CPUs. You have desktop CPUs, that is for traditional desktop computers. You have Intel Core and AMD Ryzen series that are for different types of computer. You have enterprise CPUs that are for servers and data centers that have multiple cores and features like error correcting code memory and virtualization. You have Intel Xeon processors and AMD EPYC processors. You also have cloud CPUs. These are for cloud environments, and this is different from enterprise CPUs. Such as AWS Graviton, that is for AWS, or Google Cloud's custom CPUs on the VM. You also have AI accelerators for artificial intelligence and machine learning workloads. You have Intel Xeon Phi processors and NVIDIA Tesla GPUs, and that is what we'll see next. So a task is actually an instruction that is given for your computer to execute. And you have two types of tasks, either a sequential type, or let's say you have two types of pipelines of tasks, sequential pipeline or asynchronous pipeline. Sequential means one after the other, and the impact is that you have to wait for completion of the previous task. And asynchronous is asynchronously you can execute the tasks in parallel. Here you have sequential execution. This is right. You have sequential execution. Task 1 after that task 2, waiting for completion of task 1, and task 3, waiting for completion of task 2. And until task 1 is completed, you can't start task 2. This is sequential execution. You also have asynchronous execution, where you have several tasks that can be starting in an order, but progressing without the completion of other tasks. And you have completion statuses that arrive not necessarily in the same order as the starting order. This said, these tasks can be arranged in different ways, either sequential, asynchronous, a mix of sequential, asynchronous, and there's a way to speed up computation by doing what we call parallel programming or parallel processing. There are two types or several types of parallel programming. The first one being threading. You have a process, so that is another word of our definition, that is a set of instructions, and you have a bundle of programs. And then you have threads. Threads are subsets of a process, meaning you have a process, and within these you have several threads. And they're executed concurrently within the same process, meaning they're basically executed accessing the same resources, such as CPU cores and disk, simultaneously in the same process. They share the same memory space and resources, and they can communicate between them easier, or at least more easily. And in one thread is on a single core. Complexities like race condition and deadlocks exist in this process of multi-threading. The race condition is when you have two threads that are simultaneous, meaning you have two threads that are running in at the same time. So this is when we have asynchronous, not sequential, but asynchronous execution. They're running in the same time using the same memory space and resources. And for instance, there's the use of a counter variable. And this variable can be actually taken into account for the two different threads, and it can cause a wrong increment. Let's say it's incremented on one thread and incremented on the other thread. So this is a race condition error. And there is a deadlock condition, that is when a thread is waiting for the resources at the end of another task, and this task is waiting for the resources at the end of the previous task. So it's actually a circular wait for resource availability. For this reason, you need to create safety between the threads, and this is done through what we call locks, access to resources and threads, and synchronizers that are coordinating the events between the threads, and they can prevent race condition, ensure data integrity, and manage concurrent access to critical sections of the code. The operations that threading is good for are web scraping, video processing, and file downloading, for instance, amongst others. We do multi-threading on CPU cores, and usually we have CPU cores that have multiple cores, and that can independently execute instructions for multiple tasks executed in parallel. The good analogy for threading is the two helpers in the same kitchen. We have a kitchen and two meals to be prepared, and you have two helpers that are taking the same resources, the same fridge, the same spices, and also the same set of knives. And these elements present or are able to prepare two meals, or are able to prepare a meal with a set of different tasks that could be created simultaneously, such as boiling the soup and cutting, or boiling the water and cutting the vegetables. These could be done in the same kitchen by each of the helpers in a parallel manner. Okay, so this is multi-threading. For parallel processing overall, it's multiple tasks accessing separate resources like GPU cores, computers, and GPU cores that are isolated as well. So different computers or clusters mean that we can do this on much bigger installations than just your computer. And parallel programming, with, amongst others, multi-threading, multiprocessing, distributed computing, breaks down tasks into subtasks that can be executed independently. Then we have multiprocessing. Multiprocessing is GPUs isolated one from another with specific IPC. So IPC is the process of communication between these elements, or these GPUs, interprocess communication. Shared memory, so we're sharing the memory between GPUs. You have pipelines, you have queues of messages. FIFO is the first in, first out, and sockets for communications between these pipes, queues, and memories, as well as GPUs. And you have executing concurrent tasks with these GPUs. The analogy for this multiprocessing is two helpers in separate kitchen, which actually differs from two helpers in the same kitchen because you're not using the same resources. The operations made in processing, or enhanced by processing, are matrix multiplication, neural network training, and scientific simulations. There's a way to, let's say, rate the differences between multi-threading and multiprocessing, is that if you're looking at between threads, you have a less expensive communication than between processes, and it's also less time consuming than creating a process, because the allocation of a multiprocessing is an allocation of its own memory space. Okay. I will just... There's also one more thing, is that the communication between threads, or to switch from one thread to another, is faster than to switch from one process to another. Okay, so if we go back to this, we have parallel processing, or we have parallel programming, processing, multiprocessing, and multi-threading, or better, you have parallel programming that has under its hat multi-threading and multiprocessing. If we look at the difference between a process and a thread, we have a thread that has its resources, registers, and stack, code, data, and files, and a process is a set of threads that don't share that registers and stack, and that share code, data, and files. In order to make a summary of these definitions, while a task is a set of instructions currently executing, a process that is isolated is a bundle of instructions or programs being executed. Processes go through several states depending on their progression through the execution cycle, and a single process can contain several threads for executing multiple tasks. This means that a task is a set of instructions, that a process is a bundle of instructions or programs, and then thread is one task or multiple tasks multiple tasks that are sequential, with queues and schedules. Why? Because you know that you cannot have several parallel tasks on one thread. And then you also have multiple threads in parallel that create a process. The different types of processes that you would have, or at least tasks, are IO-bound tasks, CPU-bound tasks, and memory-bound tasks. The IO-bound tasks are input and output operations that primarily determine its execution time. So IO is for input and output. And there, the CPU mainly waits for the operation to finish instead of performing computations. There is a program with many reads and writes, with user input or database queries that are IO-bound operations, because you're just waiting for the operation to complete and you have a lot of it. CPU-bound is for parallelism. It's actually using the CPU and using the computational power of the CPU for matrix computations, image, video processing, cryptographic transformations, and some data processing and transformation. The memory bound is availability, is creating availability memory during operations. Is when you're actually bound by the amount of data that you have, or the memory according to, let's say, the amount of data that you have. IO-bound tasks can be loading and aggregation of data in data sets. It can also be queries on an app, such as Flask, or if you queried from an API. These are IO-bound tasks. You have CPU-bound tasks that look like this. You have longer CPU bursts and shorter I/O operations. Let's say a matrix computation and some of the data to read and write, but not too much. And here it could be I/O bound. You have shorter CPU bursts, let's say one matrix computation, and here you have a lot of data to read. Okay? So now that we've seen how your computer is made and what kind of processes we have due to these different hardwares, and how we can speed up computation through these hardwares and characterizing these tasks, we're going to present example packages. You can code these multi-threading and multiprocessing techniques through packages in Python. For multi-threading, you have threading, you have concurrent futures that actually is for both thread and process. You have Q that is doing intercommunication for multi-threaded programs, and you have thread pool CTL. This enables you to manage threads or the number of threads in libraries such as TensorFlow. So this actually is tuning the number of threads that you have according to the tasks in such libraries. You also have multiprocessing, that is multiprocessing, parallelization on CPU cores. You have Parallel, that is doing parallel computation for pandas data frame. And you have other multiprocessing packages such as joblib, Dask, Ray, Celery, Pathos, Vex, and Modin, and not to mention TensorFlow, Scikit, and Keras, that are other packages that do multiprocessing, or that are using parallel computation. Some of them use distributed orchestration on different distributed clusters and nodes, and not only on single machines. So that is what I told you earlier, is that, or that I will tell you later, is that we're actually using these packages to manage parallel computation on clusters, on distributed clusters. Now you also have the asynchronous packages, async, that is a Syncio, that enables you to create asynchronous tasks for IO-bound code that use using coroutines and event loops. And you have async and await, that are keywords or key commands for single-threaded tasks. For threading, we can use the threading package and give you an example of this. We have here the function name that is going to print a name1 and name2. And we're going to have the function calculation x is equal to x to the power 1 million. Is that it? 1 million. And prints only the first two digits. So we're going to time name and calculation in sequential execution. And then we're going to create threads. Thread for name, so target is equal to name, and thread for calculation, target is equal to calculation. And T1 is equal to time.time, and we're going to start the first thread and the second thread, th1.start, th2.start. And then we're going to ensure the completion of these two threads, th1.join, th2.join. At the end, we can see that the completion of the program in sequences is 130 seconds or milliseconds, and the completion of the threaded version is 20 seconds. So that's a six-fold speed up. The multiprocessing package is import multiprocessing. We're going to define the CPU-bound task. Here it's taking as argument name and seconds. And we're going to print the name and sleep for some seconds, and then print the name again. We're going to create the processes through multiprocessing.process using the CPU-bound task, and create the argument for task 1, sleep 2 seconds, task 2, sleep 1 second, and task 3, sleep 3 seconds. We're going to do for processing processes, process.start, start all the processes, and then do a join. The join will ensure that the processing have finished. And this should create a series of threads that will be completed in these times here even though they started at a different moment, because you probably started first this one and then this one and then this one according to this loop. This is actually not using GPUs; it's using CPUs for it's using several CPUs. So then for the multiprocessing package, again, we can try to create a image processing. And we're going to use the pool and CPU count that we're going to find here. We're going to first process the image function to apply a filter to an image. And then we're going to define a main function that is going to create a pool of worker processes that is going to process the image with the image path that we've loaded, the list of image paths that we've loaded. So this is with pool CPU count as pool, results is equal to pool.map process image path. And then we're going to print the results, and this would have multi-processed or at least multi-threaded actually multi-threaded, multi-processed in this case. Create a pool of worker processes. Sorry, created a pool of worker processes. Now you also have the concurrent futures. The concurrent futures is going to be used in the same way. We're going to create a thread pool executor with 4 worker threads. And we're going to have concurrent future, or with concurrent futures, thread pool executor max workers is equal to 4 as executors. And we're going to have task names, task 1, 2, 3, 4, 5, and futures executor dot submit task name for name in task name, and the results that are future.result for future in concurrent futures as completed futures. And we're going to print all the results and tasks completed in the different threads, or at least pooling worker executors. Okay, so we also have, we've seen now how to use some of these packages and understood the different technologies. And we're going to talk about multiprocessing through another technology, that is GPU. GPU is graphical processing unit, and there's a difference between CPU and GPU. CPU have small number of powerful cores, 2 to 8 cores for complex calculations and data processing and running applications. And GPU have graphical processing, this graphical processing unit, have a larger number of simple cores, ranging from hundreds to thousands. And this is for processing graphical data and performing parallel computations on matrix operations, image processing, and simulations. The physical difference between CPU and GPU is seen between the CPU here, core 1, core 2, core 3, core n, where you have a memory of the CPU and you have caches inside of each of the cores, and a GPU where you have a lot of different cores here, and it's created through a set of multiprocessors and clusters and a specific memory that is the memory of the GPU. So here within a single GPU, communication happens at the chip level between the GPU cores, and on modern GPUs, it consists of multiple streaming multiprocessors, each containing multiple cores. Communication between these cores occurs via shared memory and high-speed interconnects within the GPU chip, and this speeds up computation. So the physical difference between CPU and GPU is also the fact that the GPU has its own memory. Here we have the multiprocessor, and we have a device memory into our GPU, so multiprocessors and device memory. And then we have the main memory that is linked to the device memory and also to the CPU. So that is basically how this also communicates. we have here the NVIDIA version of GPUs and the difference between the CPU and the GPU. There's also what we call the TPU, that is tensor processing unit, that we're going to talk in the side tools of this workshop. The comparison on uses. CPU is for general purpose computing. You have sequential processing with traditional software applications, web server, database, basic computational tasks. You have serial and lightly threaded applications where a workload cannot be parallelized and have a small number of threads. And you have memory-bound tasks, such as where if performance bottleneck is primarily memory access rather than computational power. Also, you have GPUs, parallelizable tasks, compute-intensive tasks, deep learning and AI, and graphics rendering and visualization. So parallelizable tasks, workloads can be divided into smaller tasks and can be executed simultaneously. Compute-intensive tasks are heavy mathematical calculations such as matrix multiplications, convolutions, and floating point operations. And then you have deep learning and AI, where training and inference in deep learning models can be taken into account, process large amounts of data in parallel, faster training times, and lower latency during inference. For the graphics and rendering and visualization, you have computer graphics, including 3D rendering, gaming, virtual reality, and CAD, computer-aided design, and CAM, computer-aided manufacturing applications. And you could also use MapReduce operations, but this is the, let's say, basic of parallelizing tasks. Now, for hardware selection, this is an important part. We've seen the comparison of uses or the choice of hardware, CPU or GPU, but there are other specifications that we can take into account while selecting a CPU and a GPU model. Performance, memory capacity, memory bandwidth, power consumption, and cost as well. And this has to be specific to your requirements and budget. And you also have specialized hardwares such as tensor cores in NVIDIA GPUs for deep learning tasks. If we look at the speed up between a CU-ML GPU and a scikit CPU, we have for 10 million points a speed up of 88 times, a speed up of 88 times between these two elements. So that's a big chunk, or a big step, let's say, meaning that for, let's say, you compute the difference between this and 88 hours, how many days is this? 24, let's say from 1 hour to 4 days difference. Okay, so as to summarize what we've done since the beginning, we have talked about how your computer is made, the hardware, the different type of tasks, and the different threads and processes, how we can parallelize computation, and what are the different devices and hardwares on which we can do that, and how to choose these devices according to tasks and specific requirements. As a summary of how to choose the CPU and GPUs, we have the actual performance difference between CPU and GPU that is based on hardware specifications, library optimization, and size of the input data. For large-scale computation and highly parallelizable tasks, we have GPUs that often provide significant speed up. And for smaller data sets or tasks with limited parallelism, the overhead of transferring data to and from the GPU may negate the performance benefits. So we would use CPU instead. It's essential to benchmark and profile both CPU and GPU implementations for specific tasks to determine the most suitable hardware and software configurations for optimal performance, and organizing tasks through different types of processes. On an MLOps viewpoint, CPUs are beneficial for data preparation, feature extractions, and small-scale models, whereas for hyperparameter tuning, both are welcome. And for TensorFlow parallel processing, GPU is better. So pieces of code now, because this is also what is important in this, and that might be the key point in using this at, let's say, low-level computations, but in order to not necessarily know the entire story around our problem. So we can use some of the packages that exist for GPU. Rapids is using CUDF, that is CUDA data frames, and it is GPU accelerated and mimics Panda API. You can perform data manipulation, filtering, aggregation, and it's leading to significant performance improvements over traditional CPU-based pandas. Here it would be XDF is pd.dataframe, and XGPU would be cudf.dataframe.from pandas of XDF. Then you would create a DB scan and a CUML DB scan, that is CUDA ML. And the DB scan is the density-based spatial clustering of applications with noise. And you could fit predict this clustering on the DB and fit predict it on the XGPU with the DB GPU. Or let's say fit predict the DB GPU on XGPU. And this accelerates 150 times the computation, or supposedly 150 times the computation. So that is the rapid, or CUDF, CUML package. You also have the QPy package, import QPy as CP. You have cp.random.rand, and then the B matrix, and you can do a dot product with CP. You also have a with tf.device GPU 0 on model.fit. You could actually also do on model and model.compile. That is how to use specifically your first GPU on training the model. So sorry, I forgot to explain that this is a Keras dataset, and we have a preprocessed data xtrain and xtest. We're creating a neural network with a loss function and compiling the model. We could have compiled the model with tf.device GPU0, but we're also fitting the model with this xtrain, ytrain, and model.evaluate our model. So this is how to use it on neural network. This specific command with tf.device GPU GPU1 is specifying which of the GPUs you want to use. You could also use CPU 0, run operation on the CPU, model.predictxtest, and we're going to just show this element without the slides. And you could also run the element, or run the operation on the CPU as well. So this predicts or shows that in the future you could probably organize CPU and GPU operations according to the tasks. Here we can do a with TF device CPU 0 instead of using CPU 0. And you could also use automatic assignment for devices where it dynamically assigns available devices based on the execution environment. Otherwise, you can also automatically choose GPU if available and fall back on CPU if it's not. With device GPU 0, if tf.test.isGPU available, else device CPU 0, and predict the model, model.predictxtest. Just know that there is an extended documentation of TensorFlow in order to use these several options of tuning your use of CPU and GPU through the different tasks in MLOps. So now we're going to talk about the devices of where our GPUs are available. You have NVIDIA that produces its own line of GPU computing systems, such as the NVIDIA DGX systems, and which are specifically designed for deep learning and AI workloads. You have Dell, HP, Lenovo that offers workstation platforms with NVIDIA Quadro and NVIDIA Titan GPUs. And you also have Apple with AMD Radeon Pro and AMD Radeon Pro Vegas. And this enables CUDA-enabled application, even if Apple doesn't support CUDA officially. This can also be useful for you guys on your projects. There are side tools that you could use in limiting time and computing power used in loading and training. You can use generators that are going to load a batch and train a batch in the meantime, but not load all the data in your data sets in order to fit your model. That would be model.fit generator from Keras. And you can see here that it's using the generator train generator. That would be a generator that was created before our fit generator, sorry. And you also have the pre-processing with map in a multi-threaded fashion. And here you can create a TensorFlow dataset, tf.data.dataset.from tensor slices from an image path, and apply a mapping of loading images with a non-parallel call, usually is equal to -1, but here can be equal to tf.data.experimental.autotune. And the number of parallel calls equal -1 is enabling the multi-threading of the processing of your dataset, of loading and processing your dataset. So let's say you have an operation on your dataset. Imagine this is resizing the image that you're loading. It's going to say, instead of doing this in a sequence, we're going to do this by batch of 3 in different cores. And so it's going to divide by 3 or more the computation time. Now, we've talked earlier about TPU. TPU stands for Tensor Processing Unit. It's an application-specific integrated circuits. TPU were designed by Google. They were started in 2015 and made public in 2018. And they are available as a cloud or smaller version of the chip. Cloud TPUs are very fast and performing dense vector and matrix computations to accelerate neural network machine learning on the TensorFlow software. And of course, TensorFlow is an open source machine learning platform built by the Google Brain team. And it helps developers, researchers, and businesses to run and operate AI models on high-level TensorFlow APIs backed by cloud TPU hardware. TPUs minimize the time to accuracy in training large and complex neural network models. And with TPUs, deep learning models that previously took weeks to train on GPUs now only take hours on TPUs. The Liaison Google Colab. You have a possibility to use GPU on Google Colab. Connect button, change runtime type, click on T4 GPU. And we're going to go to this page to show you the difference between the presenting share screen of the TensorFlow Colab. So here we basically have enabling a testing the GPU, and we're going to use device name tf.test GPU device name, and we are going to create a CPU version of the function and a GPU version of the function using the CPU here and using the GPU here. and we're going to create a feature selection or a convolution of the set of image GPU or random normal distribution set, and return the tf.mat.reduce sum of net GPU. And if we print the processing time of these operations, we see that GPU speeds up over CPU 35 times. So basically, that is one of the uses of your GPU on Google Colab. Now, let's give example on ML algorithms. In XGBoost, you can use GPU through the parameters. Tree method, GPU hist, GPU ID is equal to 0. Tree method is going to specify the method. Sorry about this. Tree method is going to specify the method used to build trees and set this parameter to GPU hist to enable GPU acceleration. And the method builds histograms on GPU, which can significantly speed up training. GPU ID specifies the GPU device to use for training, and this sets this parameter to the index of the GPU device that you want to use, e.g. 0 for the first GPU and 1 for the second, and you can also specify comma-separated indices, such as 0, 1, and 2. And predictor specifies the type of prediction algorithms to use on GPU as well. So you can set this parameter to GPU predictor to perform inference on GPU, and this can speed up prediction for large data sets. And you also have other features to use in these parameters on XGBoost models. And you also have other models that are using these techniques, but this is an example. You also have example on deep learning methods and packages. For Keras, you can compile the model as well instead of just fitting it with GPU, but you would create a model, pre-process the data, create the model, have the loss function and the compilation of the model, and with tf.device with a GPU or your first GPU, fit your model, X-train and Y-train, and this would speed up computation. If you install TensorFlow GPU on your computer, you could also use TensorFlow. And here you would create a model, a Keras model, and use what we call the Myers strategy for multi-GPU training. So strategy would be tf.distribute Myers strategy, so for multi-GPU training and not just one GPU training. And then use the strategy scope. With strategy scope, model dot is equal to create model from the define model function, and create the loss function, the optimizer, and model dot compile our model in order to do that on several GPU. And also actually model dot fit should be inside the strategy scope. Then we can also create a set of functions that will be used or that will be executed on CPU and others on GPU, pre-processing of the data on CPU and model training on GPU. And then we would create a main function that would actually use the strategy tf.distribute.Myers strategy for training the model with the X-train, Y-train, and the strategy as a parameter in training the model. The other elements being pre-processed data and evaluate model that are automatically on GPU. So how does it work on TensorFlow? You have TensorFlow graphs, computational graphs. These graphs, and wait, actually, there was, first of all, in order to have these graphs, you can put a decorator at tf.function before your functions, and this would create graph optimized function for Python functions. So computational graphs are executed in a distributed manner with each device execution, and it's assigned part of the computation. These graphs include the layers operations, and tenses that are involved in your model's computation. If you create a model with a scope of a distribution strategy, TensorFlow automatically replicates the model across all devices specified by the strategy. You have variable mirroring, where any training variable or trainable variables, such as weights and biases, created within the scope of the strategy are automatically mirrored across all devices. This ensures that each device has access to the same set of variables, and updates to these variables are synchronized across devices during training. Data parallelism is that during training, TensorFlow partitions the input data into batches, and each device processes a subset of these batches independently. Each device computes the forward and backward passes for its batch of data, and gradients are aggregated across all devices to update the model's parameters. So then, throughout the training process, TensorFlow ensures that all devices stay synchronized, and this includes synchronizing variable updates, gradient aggregation, and any other communication between devices. Synchronization mechanisms such as collective communication primitives, such as all-reduce, are used to coordinate the computation across devices efficiently. If you look at collective communication primitives, we'll talk about this after the graph. This actually is a graph of a computational graph of TensorFlow for a CNN. You have the different computations that have to be made through your CNN, and it's organized in a way so that it optimizes computations. Collective communication primitives, as we talked about earlier, are operations that involve a group of processes or nodes in parallel and distributed computing environments. It's essential for coordinated and synchronizing activities. You have broadcast, gather, scatter, reduce, all gather, all to all, and barrier. For instance, broadcast is one process sends a message to all other processes in the group, and gather would be each process sends its data to a designated root process, which gathers all the data into a single buffer. All these operations are collective communication primitives that enable you to coordinate and synchronize the activities. The primitives, they're building blocks for many parallel algorithms, and they're supported by parallel programming frameworks and libraries. They help in achieving synchronization, data exchange, and coordination among processes efficiently. Now that we've seen this to a certain degree of details, we know that we can deploy these parallel computing on single machines, as well as deploy them on clusters of machines through different kind of packages, and also on the cloud. On the cloud, we have two types of machines: general purpose compute instances and GPU instances. For AWS EC2, you have instances such as T2 and M5 and M6G that are providing CPU memory and networking resources for a wide range of applications. Google Cloud Compute Engine with VM such as N1 standard and E2 standard that provide general purpose computing resources, and Azure virtual machines like DV2 and DSV3 that are designed for general purpose workloads. Then you have GPU instances, AWS EC2, that provide P3 family optimized for GPU accelerated computing tasks, Google Cloud Compute Engine for Google Cloud Platform, GPU instances like N1 HiMem HGPU, and Azure virtual machines as well, NC, ND, and NV, that are for GPU accelerated workloads. We have existing computing optimized or memory optimized as well. Now we're going to be storing a LiDAR model. This is a, let's say, side improvement on computation costs and memory, but this actually must or probably might be an important side or aspect of this problematic. Sometimes you want your model itself to be lighter, and you can use quantization or pruning. Quantization is when you decrease the precision of the object in which the model's parameters are stored. And it reduces accuracy, but not by much. And here, in this case, you have a converter that is tf.light.tf converter from Keras model baseline. And you optimize converter optimizations is tf.light.optimize default. And you get the converter model quantize tf light converter.convert. And the model size is divided by 2. You can also use pruning that identifies and removes unimportant weights, and it reduces the ladder model size by 2 again. So if you have here a certain number of weights in the neural network, you are reducing the number of weight by removing some of the neurons. So as we've seen these tools, there are also very widespread tools in order to create parallel computations and parallel processing through ETL. You have PySpark and PyTorch. So the ETL is extracting, transforming, and loading in data engineering, where the entire pipeline can benefit from accelerations. On the cloud, you can create data pipelines where you have several tasks that can both, or at least processes that can run in parallel, and also tasks that can be parallelized. This is a data flow example of a machine learning, or at least data flow pipeline. And you can run this with some SDKs or some Python frameworks, such as PySpark. So Apache Spark is a computing framework for processing large data sets and complex algorithms in parallel computing with a distributed architecture. PySpark is the Python tool that enables, with Apache Spark, partitioning, caching and persistence, broadcast variables, parallelism and cluster configuration, optimize transformations and action, map and filter, optimize joins, use UDF and vectorize operations, and optimized algorithm and libraries. So basically, if you have your GB of data, you create your Spark context, and you have a cluster manager that is a resource manager for your different workers that are going to make the computations. And you create partition in your data in order to have your data processed on different workers. The Spark context is Python Scala code, and the workers are where you have your computation power. So this is basically parallelized. Okay, this could be MapReduce operations, and these could actually be aggregated afterwards in a certain way that is the way PySpark aggregates the data throughout different steps. If you look at worker nodes, you have executor, runner, and each executor has a cache and different tasks. This is a coarse-grained executor backend, and this is basically how the worker node is organized. Okay, so this is an example of all the different tasks that PySpark can create. You have here the opening of a Spark session, sparksession.builder. You have the loading of a large data set from HDFS, a Hadoop distributed file system, and this is a spark.read.csv. You have the partitioning of the data sets to optimize data locality and reduce shuffle operations, df.repartition, caching and persistence, df.cache, and broadcast variables. You can also do parallelism and cluster configurations with executors, cores, and memory allocation, which is what we see just after that, and optimize transformations and actions, df.filter, filter.select, and mapped reduced by key, which is basically mapping, select.map. It's mapping the data set with a 1 for each element, and then it's reduced by key summing on the x plus y keys. Then you have optimized joins, df.join, and use of UDFs and vectorized operations, as well as optimize algorithms and libraries. Here, that is a linear regression. but you have much more complex tools as well. So for the use of parallelization across the different nodes, clusters, and workers, you have here the configuration spark.executor.memory that is 4 GB. And the first one, that is this first one, sets the amount of memory allocated to each executor, that is to say clusters. The second one, spark.executor.cores, is 4. This configures the number of CPU cores to allocate to each executor for parallel processing or parallel tasks. And the Spark driver memory, 2G, this sets the amount of memory allocated to the driver, and it coordinates all the executors in the cluster. So this is basically how, for a simple task, you can configure your Spark session to work in parallel processing. And here we're just creating a UDF to compute the square of x. There's also PyTorch, that is an open source machine learning library for Python developed by Facebook's AI research lab, the FAIR. And it provides a flexible and efficient framework for building and training deep learning models with support for dynamic computation graphs, automatic differentiation, and gradient computation, as well as GPU acceleration. If we want to look into the PyTorch code, here we have an actual use of the GPU in our step 6, move data to GPU if available for GPU acceleration, input target, inputs.CUDA, targets.CUDA if torch.CUDA is available, else inputs or targets. And this will actually use the GPU. Is going to move data to GPU. Okay, and this task would actually be to define a neural network and train a neural network. Okay, so now we've seen several packages and several examples of GPU acceleration and multi-threading on CPU, and an organization of tasks on CPU and GPU according to these potential packages, single device, several clusters, or cloud as well instances. We've talked as well of the different hardwares that we could use and how to choose them. And now we have to talk about monitoring the different metrics that could enable us to see where are the bottlenecks in our pipelines and where we can improve time and computation. So in monitoring, this is kind of advanced, and for those who are not interested in these issues, the first line is actually the most important. Resource utilization. We have to monitor CPU, memory, disk I/O, and network I/O. But you could also monitor thread process activity to track the activity of individual threads and processes, including the start, end time, execution duration, and context switches. You can look at concurrency metrics, measure concurrency metrics such as the number of active threads and processes, the concurrency level, and the throughput to assess the level of parallelism and concurrency in the system. You could look at thread process synchronization, monitor synchronization primitives such as locks, semaphores, semaphores being as in the road. I'm telling you that you can start or not the task. And conditions variables to identify potential contention points and deadlocks, as we said earlier. Track the usage of synchronization primitives, analyze wait times and contention levels to optimize synchronization strategies and avoid performance bottlenecks. We could do thread process interactions, analyze interactions and communication between threads or processes, include message passing, shared memory access, and inter-process communication. Monitor message queues, shared memory regions, and IPC mechanisms to detect message backlogs, contention, and potential race conditions. We could also do performance profiling using performance profiling tools and analyze the execution behavior and performance characteristics of multi-threaded and parallelized applications. We can profile CPU usage, memory allocation, I/O operation, and function call traces to identify hotspots, inefficient algorithms, and performance bottlenecks. There's also a way to do thread and process pool management, to monitor thread process pools and thread pool queues to ensure optimal utilization of worker threads processes and efficient workload distribution. There's a way to track queue sizes, task execution times, and thread process pool metrics to dynamically adjust pool sizes and optimize resource allocation. Last is monitoring frameworks. We can utilize monitoring frameworks and tools that provide real-time monitoring, alerting, and visualization capabilities for these applications. And they can include built-in support for monitoring concurrency metrics, performance counters, system resources, as well as customizable dashboards and reporting features. This is actually what we can see here with Prometheus that is dashboarded by Grafana. Here you have a number of processes, CPU usage, write bytes, read bytes, and this ends the monitoring section. We're now going to start a good practices for reducing computing cost in code. This is a large section that will actually be our last section. And in this last section, this is a piece of, let's say, information that is a bit on the side of what we've seen so far, but has the same purpose as speeding up computation and reducing the computing costs, either in the code or in the use of in the uses of our hardwares. And also on the cloud platforms, because your algorithms can be accelerated through hardware, but also through code efficiency. So we're going to optimize algorithms and data structure. You can choose your algorithms and data structures that are efficient in terms of time and space complexity. Use algorithms with lower computational complexity whenever possible. Optimize data structures to minimize memory usage and improve access times. You can minimize redundant computation with cache intermediate results, avoid recalculating, and use memoization technique, that is caching results in different ways. You can parallelize and distribute work on CPU cores or GPUs. Leverage distributed computing frameworks like Apache Spark or Dask for large data sets. Consider cloud-based services for scalable and distributed computing resources. That is actually important because you can use non-permanent resources as well. Batch processing and streaming. Batch process that whenever possible to reduce overhead and improve efficiency. Implement streaming processes. Use windowing and buffering mechanisms. And you could also optimize I/O operations. Minimize disk I/O and network transfers by batching or aggregating data. Use compression techniques, use caching mechanisms to reduce the frequency of the disk read and writes, and resource management and auto-scaling. You can monitor resource usage, such as CPU, memory, and storage, implement auto-scaling mechanisms to dynamically adjust computing resources based on demand, and leverage serverless computing platforms. You can also do cost-aware programming, minimizing expensive API calls with designing code with cost consideration or data transfers. You can consider factors like pricing models and usage pattern in choosing cloud services or a cost-effective solution. And you can monitor and analyze cost metrics for efficiency improvement. This actually is a section that we'll see just a little later in the workshop. You can clean and create modular code as well. Write clean, modular, and maintainable code that is easy to understand and debug. Refactor code regularly to remove redundancy and improve readability. Document code to provide clear explanation of its purpose and functionality. Now, the impact on billing and workflow is following this section because you can create efficient workflow through these advice and also reduce billing. Be it on a single device or on an on-premises installation or on the cloud or even in hybrid settings, you can look at processing time and responsiveness, parallelization, concurrent execution of tasks, CPU cores, GPUs, as we've seen earlier, and other resources, as well as data processing, model training, or batch processing, and this can benefit from increased throughput and faster turnarounds. However, if you're coordinating parallel tasks and managing dependencies between them may introduce complexity to the workflow, requiring careful design and implementation to ensure correctness and efficiency. Autoscaling and resource management, of course, you can autoscale and schedule your workloads. Billing considerations. You can use cloud on usage, compute instances, storage, and data transfers. You can do multi-threading and parallelization. It can impact billing, the duration and intensity of resource usage. If you're running tasks in parallel, it may increase the number of compute instances on our virtual machines provision, leading to higher costs, and you have to strategize and optimize resource usage to minimize costs while meeting performance requirements. And this is basically avoid over provisioning and underutilization. And there's also a autoscaling and workload scheduling for billing consideration. So if we're looking at a cloud platform, here we have the high-level billing, where we're looking at the billing per month for each of the services that we have. But we are not seeing the fine-grained billing. So we can try, or it actually exists, but if we want to predict our, let's say, resource level billing, we can use the Google Cloud Platform pricing calculator. And it will, on each of the tools, ask us what are the instances that we're creating and make a plan on basically the billing that we would have at the end of the month. This is a graph that it outputs when we have done this pricing calculator to see the different resources that might be linked to each other and how they use. And there's also a list of the different resources or unit resources that we're using here. These are preemptible disks, and it shows how much CPU, RAM, and disk is used as well, and what price it is. As of a conclusion, we've actually gone through a lot of material in a very short time, and I apologize if this has gone too far or too fast. In any case, we have types of operations that are asynchronous versus sequential, and through these choices, we can do an organization of parallel programming, multi-threading, and multiprocessing that are under the hat of parallel programming. It depends on the type of operations, the high-level packages that we have in SDK, in Python languages, for instance, the fine-grained organization and orchestration of the different tasks that we would have in these programs, and the bottlenecks that can be created through these elements, as well as the monitoring that we make of these tasks and the different metrics associated with our types of operations. There are as well hardwares that we can choose from in order to speed up our computations, the RAM, the CPU, the GPU and VRAM, and the TPU, and our devices, whether we are on a single computer, a distributed cluster on premises or on the cloud, with different computers and chip runs and clouds. So these were my findings. You have useful links here for code costs, multi-threading, and multiprocessing. And if you have any questions, I'd be very happy to answer. So let me just look at this. So basically, it's the first question that we're going to take. We actually don't see my face during the whole webinar. We've seen the face during the workshop just till the, let's say, second, third, and then I had to remove my head because I had to remove I kept my head on my shoulders, but I had to remove my head from the screen because there were some text that my face was hiding, and the text was more important. I apologize for this. There is also a question from Salomon that is it right to think that the stronger your CPU in speed and number, the lesser the demand is placed on your RAM? So basically, CPU and RAM don't have an inverse relationship. And the RAM is volatile memory, and if you don't have and a strong CPU doesn't mean that you have a lot of memory in the CPU. So it will actually depend on the performance dynamics of your CPU. And it also doesn't necessarily reduce the need for RAM. So another another question from Salomon Tabo. Google Colab still limits your computational ability. I tried and was often told that I have run out of my computational resources. Meanwhile, the code hasn't finished running. This actually might be true because you have a certain limit of computation, even if you have a GPU. Remember that you could probably let run your programs a long time. Side tools for you guys on Google Colab. If you close your session, you have 90 minutes of possible computation. And if you don't close your session, your algorithm can run 12 hours. So Joseph, you're looking for another view for AMD Radeon supported package. Okay. I'm actually looking for this, but I would like you to specify your question maybe. At least you probably have PyTorch. And I'm looking for other ones. But that is already an answer. There's a question from Timea. Sorry. During our project, we have to also make decisions about how do we manage our resources for our models, like the threads, computing, and if yes, how in depth will this be? Actually, you probably would have to make a decision like this, but it will depend on the data set that you will get. I suggest that you actually try in order to have this as an example in your portfolio in any case, and the depth of it depends on how much work you want to put in it. Remember that your portfolio is actually a very, let's say, a very important element in your finding a job and career assessment as well. The workshop material will be, so because the workshop material was good and compact, covered many details. Thank you very much for this, Timea, and it actually will be available as well, so you guys can choose from these and also try and research on a lot of different resources. It could go from very simple ChatGPT researches towards data science or articles, scientific articles on these issues. There is a very good, not tutorial, but explanations on TensorFlow and Keras websites. And you could also just do a Google research as well, which is a very good way of, and Stack Overflow as well is covering a lot of these subjects. Hi, so I know that my friend, the CEO of Reality Virtual, is using GPUs a lot to lay pictures onto a 3D structure to create virtual reality. This process can be optimized with AI to lay pictures onto a 3D structure. I apologize, I actually don't understand your question. Could you please, Marius, repeat this question or try to rephrase it? I can see Joseph has been saying there is a combination of operating system and GPU manufacturers that makes it difficult to choose a path. Could you please, Joseph, enlighten us or let's say expand your explanation on this question? All right. So I can see you guys don't have more question. If you want to ask a question, you can do this through the Slack. There is going to be a recording posted on YouTube as well as the slides. So I can see Nicholas back the planet. So you can, so let me just look at these questions. I'm sorry, Marius, I see that you wrote something else, but this looks a very strange addition to. I'm not sure I understand your questions, but I will show them because I think it's mapping pictures onto a 3D structure to create virtual reality. Their mission is to back the planet. And I don't actually really know what this means, but I know he needs Unreal Engine a lot. And I just talked to him directly if he's using AI and machine learning pipelines. So this is basically a comment that I might not be understanding through translation. And in this case, I apologize for not being able to respond. So, Timea, do you have tips for us how we can start to practice this workshop material with an easy example? You could actually try to create a neural network algorithm or just try the XGBoost with the parameters. And this could be a very easy example following the architecture that you want to use and using the tf.distributed.meyer strategy on Google Colab, because you probably, or maybe you do, have NVIDIA, but I'm not sure it's a, let's say, widespread acquisition on our learners. If you want to, I don't know, it depends. I can see Nicholas has said, I meant to parallelize the computation of several batches. One batch in training model in batch corresponds to a computation with one set of weight bias values. Then how is it possible to parallelize? So, for instance, if you want to load batches, or if you want to train your model, you're going to load with the fit generator, with a generator, one batch after the other. And you're going to have in memory fewer batches than the totality of your data set. If you do this, so this is going to be a sequential operation. The loading of the data set would be a parallelized operation where you're using a TensorFlow argument in a mapping function, or at least using, TensorFlow dataset and mapping a TensorFlow dataset with a non-parallel calls that is going to say that you're going to use multi-threading in order to load and process your data. I'm not sure this answers the question. Okay, I get it. This comment is actually strange, but it's okay. Back up the planet. Did I answer your questions, Nicholas? All right. Then if I have answered your questions, remember that you will have a set of YouTube videos that are not just on this specific workshop, and you will have a set of elements that can be used, such as the blog of data scientists, the podcasts, and also some of the videos for the learners. You have a Notion page and a career management website. And at 12, you also have a career workshop. There's a question by Mohammad Amin. Which cloud platform do you prefer to run a Descent project on it, like our projects for data scientists? It's actually a biased question because I don't know AWS and I know GCP. But if you asked other people, they would say the other way around. Indeed, the cost function for each batch cannot be computed in parallel as a result of one batch depends on the result of cost function of the other. No. Yes, but you're not doing this on, you're actually, this is why it was strange. It's not done on training. It would be done on loading, for instance. But this actually is a good question, the way it's phrased, and I might be able to answer this after the workshop to give you an answer on the chat of the YouTube video. I apologize, Marius, for the answers I gave. It's actually that I don't understand the vocabulary that you've used, such as planet and another word that was used in here, Unreal Engine. So that is virtual machine. I think there might have been a problem in translation. and I would have loved to answer your questions, but I didn't understand. I actually haven't gone through the AI models in creating virtual reality because this is going way beyond our subject right now. Could you access the slides? Yes, of course. You will be able to access the slides right after the YouTube video is posted on the YouTube channel. All right, then I will close this workshop, and I apologize for those I didn't answer the questions. You will find an answer to those questions I can answer and understand at the end of the or on the same page as the YouTube channel. And for the others, thank you very much for your questions, and hopefully you will find this material useful. I enjoyed very much giving this workshop, and I will try and create new materials that would be useful for you guys in creating your project, either in data scientist or outside of data scientist. I wish you a very good end of the week, and I hope to see you again in these workshops and during the classes. I will say again that you guys have resources such as the YouTube channel, the podcasts, and also the creation of a blog where we have articles. So I will. I can see that Marius said that backing up the planet was having a virtual copy of certain monuments on our planet. I apologize, Marius. I actually think this is going a bit out of the realm of our workshop, and I will thus not answer this question, but I encourage you to research on it, and it might be actually a very interesting issue to talk about. Have a nice day, and see you later.